Best laid plans of mice and men. The technology we need for writing proofs about programs still isn't here. So now that's going to be our week 5. Today I'm going to show you how to write a sorting algorithm from first principles in Ask, which is starting to look a little bit like real programming. Specifically, we're going to write an insertion sort, which isn't a very good sorting algorithm, but it is a very simple one. So here I've set up a data type for lists. I've written it in a slightly different way now that you're comfortable with the basics. The const constructor is now written as an infix operator using the colon symbol. Previously, constructors of data types have always been written as names with a capital letter, but now the colon symbol is also a constructor and it's written infix between 2 arguments. And on the next line, you don't have to worry about this, but this is telling Ask's parser that colon is an infix operator, that it brackets to the right, and what its precedence level is. I've also got booleans and the if-then else operator that you wrote in last week's exercises. Okay, now we need to start by writing an insert function that inserts an element into an already sorted list. It needs to scan along the list, comparing each entry in turn with the element that we want to insert. As long as what we're trying to insert is bigger than the current first element, we keep looking. And as soon as we hit a point where the thing that we're trying to insert is smaller than the first element, then we insert it at the front. So for this function, we're going to assume that the starting list is already sorted, otherwise it won't work properly. And we need to make sure that it preserves the property of being sorted. So if the input list is sorted, then the output list will also be sorted. Okay, so this is a bit of a complicated function to write. The first choice I'm going to make is I'm not going to specialize this whole thing to sorting lists of numbers. Instead, I'm going to write it so that it can sort a list of anything, but I have to take as an extra parameter a function that does the individual comparisons for me. And at the end, when I want to sort a list of actual numbers, I'll have to supply the function that compares numbers. Okay, so the insert function is going to take as its first input a comparison function, which itself is going to take 2 elements and return a Boolean that says whether the second is bigger than the first. Then the second input to insert is going to be the element that we want to insert, and the third element is going to be the starting list, and then the output is going to be the list with the element inserted. So this is our type signature. Now let's start to define it. I'm going to name the first parameter, which is the comparison function LE for less than or equal to, because that's what I want it to mean. The second element that we want to insert, I'll call X, and the list I will call Ys. Now we're going to write this function by recursion on Ys. So I'm going to start by writing inductively Ys, and then I'm going to write from Ys. Now ask tells me that Ys is either empty or it's a head const onto a tail. Now the first case of this is easy. If we're trying to insert an element into an empty list, we don't have to do any comparisons because we're just going to get a list with 1 element. So in this case, the output is going to be X const empty. Now in the second case, we're going to have to do some work. So we need to compare the element we're trying to insert, X, with the head element of the list. And then we need to do 2 different things depending on whether it's less than or equal or whether it's bigger. So for this, we're going to use the if-then else function that we wrote. So I'm going to write if-then else less than or equal X head. Now, we have 2 cases, one where X is less than or equal to head, that's the first one, and one where X is bigger than head, that's the second one. So in the first case, we found the place where we need to insert the element and we insert it at the front. So for this, we can stop. We don't have to do any recursive calls, and we can join the element X onto the front of the list like this, X const head const tail. And const brackets to the right. So secretly, this is X const head const tail like this. In the second case, we have to do a recursive call. So what we're going to do is we're going to recursively insert X into the tail list and then join head back onto the front. So I'm going to say head const insert X tail, and I also have to supply LE again. And this is completes the definition of our insert function. Okay, now that's our function that inserts a single element. So now we can write a function that sorts a list. And we're also going to do this for lists of any type. So we also need to take a comparison function as input. So now as our second input, we take the initial list, which is not sorted, and then we output the list which we get by sorting the input. Okay. We're also going to do this by recursion on the input list. So I'm going to write inductively x's and then from x's. So in the first case, we're trying to sort the empty list. Sorting the empty list is very easy because the empty list is already sorted. So in this case, I can just return empty. Now, the second case is the interesting one. Now, what I can do here is I can recursively call sort on the tail. And then that results in a list that's sorted. And then once it's sorted, it's in the form that our insert function works for. So I can recursively sort the tail and then use insert to put head in the right place in it. So I can do sort le tail, and then I can do insert le head of that. And that's our sorting function. Okay, now in order to test this, I also need to write the less than or equal to function for natural numbers. So here's quickly the definition of natural numbers. Less than or equal to is a function that takes two natural numbers and it returns a Boolean telling you whether the first is less than or equal to the second. We're going to do this by recursion on the first input. So I'm going to write inductively m, and then I'm going to write from m. Now, in the first case, we're checking whether 0 is less than or equal to a number, but 0 is less than or equal to any number. So in this case, we can just return true. Now, in the second case, we're trying to check whether some successor is less than or equal to some number. To do this, we need more information. So I'm going to write from n to learn something about the second input. Okay, so now in the first case here, we're checking whether a successor is less than or equal to 0, but the successor of anything is always at least 1. So this can never be true. So I can just write equals false here. Now in this case, we're checking whether some successor is equal to some other successor. And you can imagine subtracting. So this is checking whether, say, x plus 1 is less than or equal to y plus 1. You can subtract 1 from both sides of that inequality. So this is the same as checking whether x is less than or equal to y. So in this case, I can do a recursive call and I can say m prime less than or equal to n prime. So this is our comparison function for natural numbers. So now I can test it. So let me just quickly name some numbers here. So 1 is the successor, define 1 is successor of 0, 2 is successor of 1, 3 successor of 2, and now I can say test sort less than or equal to, and now I can supply a list. For example, I could say 1 cons, let's say 2 cons 1, cons 3, cons 2, cons empty. And I get back the list sorted, which is 1, 2, 2, 3. Okay. That's the end of the week 4 explorations. I'm sorry that it's been a bit of a strange week of material, but we're turning a bug into a feature by giving you lots more practice at writing recursive functions in this week's exercises.